9.3, right? We gave an example on that section illustrating how you have to go about finding the unique solution of an initial value problem where the restrictions are fulfilled, right? For the Laplace transform technique to apply. The differential equation has to be linear and with constant coefficients. And then there is a minor restriction that says that if the differential equation is also non-homogeneous, the function, the non-homogeneous function on the right-hand side of the differential equation has to be a function of t for which the Laplace transform exists, right? Because step one on solving the initial value problem would be to take the Laplace transform of the differential equation. And therefore, on the right-hand side, the Laplace transform of the non-homogeneous function, if the differential equation is non-homogeneous. And we gave an example, and we worked out an example of how to find that unique solution using the Laplace transform following the 3 steps, right? Step number 1, you take the Laplace transform and use the properties. To what? To come up with an algebraic equation on the Laplace transform of the solution. Once you have that algebraic equation on the Laplace transform of y, step 2 is an algebra step. You solve the algebraic equation for that Laplace transform of y. And that takes us to step number 3, and final step in the technique to find the unique solution. And that would be to go from the Laplace transform of y as a function of s that you just found at the end of step 2 to find the inverse Laplace transform of that to get to the unique solution, end of the problem. In that, we did a problem, the problem we did on Friday, in class on Friday, was in step 3, you ended up with the sum of 2 terms. Each one of them was a rational, pretty much a rational function of s, right? And we needed to find the inverse of each, inverse Laplace transform of each. And remember how we proceed. For one of those terms, we did use partial fractions. And for the second one, we use a convolution to find the inverse of Laplace transform. Remember that property about if you had 2 functions, okay, f, little f, and little g, t, you convolve them. The Laplace transform of that convolution is the product of the Laplace transforms. And that's a very nice property that can be used most of the times to find inverse Laplace transforms, right? Because you can use the Laplace transform version of that, or the inverse. The Laplace transform of the convolution is the product of the Laplace transforms. Now, if this is, if you call this function capital F of s, if this one is some function capital G of s, right? And they're multiplying each other. If you take inverse on both sides of the above equation, you can rewrite this property like, because on the left hand side, if you take the inverse composed with the Laplace, they will cancel each other and you end up with just. So these are the same equivalent, right? This is the one that you use to find the inverse. Whenever you have the product of 2 functions of s, you are interested in finding the inverse of that product. Well, if you can find the inverse of this, and the inverse of this, g, you convolve those 2 and that will be the inverse of the product. Right? Any questions? So pretty much at this point, that takes us to the end of section 9.3. Right? We know how to solve. At this point, we know how to solve any initial value problem for which the differential equation is linear and with constant coefficients. Most generally non-homogeneous, with a non-homogeneous term or function of t on the right hand side of the differential equation. So now, what are we going to do next? Well, remember that if you look at for those of you who, we didn't see that application in chapter 5, right? But there was an application of linear differential equations in chapter 5 about electrical circuits, right? You can model what's happening on an electrical circuit. Any kind of electrical circuit, you can model that using mathematics, and you end up with a second order linear differential equation with constant coefficients. And on the right hand side, the non-homogeneous term is it reflects if you're switching on or off the circuit, right? By letting some electricity come in or come out, at which level, right? Meaning that if you switch off the whole thing, I mean, then the right hand side becomes 0, and you're dealing with a homogeneous differential equation. If you switch it on, it's not 0. It could be, and it depends on the level of intensity of the voltage that you are inputting into that electrical circuit. And those voltages could be, variable, or it could be constant. Doesn't matter, it depends on the particular application, or the particular electrical circuit that you're dealing with, right? But to know exactly what's going on those electrical circuits is equivalent to solve initial value problems where the differential equation is linear with constant coefficients, and the right hand side, the non-homogeneous, the possible non-homogeneous term that you have on the, so suppose that, you have this general, I don't know, I mean, if I go back to that section, chapter 5 that we were talking about, and I look at when they work out, let me tell you what they come up with, right? To be precise, this is what they came up with. Electrical circuit problems, they got this. And they use Kirchhoff's laws and voltage, blah, 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 blah. We end up with this, right? This one, L I double prime T plus R I prime T plus 1 over C and then you get two initial conditions, really. I mean, what are the initial conditions? And let me see what they call this. Well, whatever. So let me, you have an electrical circuit. Let me just put here this. You have a they have a resistance L. And what what are these? Well, I mean, this is how many people are electrical engineering majors? One, raise your hands. 1, 2, 3, 4. So this is for you. Have you seen this?
Not yet.
No? One yes, one no? Yes. What is this? It's an electrical C. What is the C? What does the C stand for? Because it's a capacitor. The L?
Inductor.
An inductor. I don't know what it is. What is the R? A resistor. And the E?
Battery.
It's an electromotive force, a battery or a generator. A battery or a generator, right? So the thing is that how do you create this electrical circuit? I mean, they have to give you, so the R, these are constants, right? The R, the L, and the C are the constant coefficients of this second order linear. And what is IT, the little I of T? As a function of current. It's current, right? The current on the circuit at any time. That might change, depending on. Now, so what happened, let's see, this is, What is the key thing that is going to create that current in that circuit? Power source, right? The battery, and that power source could be, look where it appears. That's a non-homogeneous term, right? That's the non-homogeneous term. It's the derivative of that power source function that creates the electrical circuit. Now, in a sense, this is they call it the electromotive force. So that changes as time changes. I mean, you can have any kind of battery that, as you switch it on, it gives you at the beginning some constant, then you switch it off, but then after that you gave an alternative current or whatever, you know, whatever. So this really, this every function of t that it could be like, say that this is t time, and so it could be at the beginning of time is off, right? Meaning that's it. Then you turn it on, the battery, and you give it a positive slope linear function for the E prime function, right? And then you switch it off again, boom, and it's off for a while, and then after that, jumps up to be, and then it could be any kind of function, right? Depends. I mean, the electromotive force that the generator or the battery applies to the circuit. So, what is the point here? In many cases, this non-homogeneous term on the application, right? Look at this electrical circuit. This non-homogeneous term on the right-hand side of the linear differential equation with constant coefficients doesn't have to be a nice function of t. It could be one of these, you know, off, on like this, off again. Now, so this is not gonna be like e to the t, or it's gonna be a constant or anything like this. It changes, right? And that really reflects the application of what's happening in an electrical circuit. about any guys in electrical engineering. I mean, you set up an electrical circuit and in a factory, and sometimes the machine needs to be off, and sometimes you turn it on with different. And you're interested in knowing what the solution of this would be, the current at any time, right? And that has a lot of applications also to electrical grids in the cities, in the countries, in the county, in this, how they interact with each other, right? When you produce electricity, it's and you use it to feed the needs of the people in a city or something like that. You wanna know, you know, what's the the current at any given time, so that you generate enough electricity so that to you know, service the city. Also at the same time, right? You also, I mean, you don't want to have a power breakdown or anything like that. So all this, and you guys in electrical engineering know that, electrical, public utility electrical companies will hire you guys to look at these type of problems and make sure that the power grid is always working properly. And you're really looking at these type of problems and making sure that all these, the solution is a nice solution to the problem, and so that the electrical power is gonna be on all the time, right? We're not gonna have a power shutdown or anything like that. So the point is that in this type of, and then of course, think of this as being an electrical circuit that feeds a whole city, right? This would be the generator, the power plant that generates the current. And that those power plants, they create electricity at different levels, right? Not all, sometimes they're off, so, and according to mathematics, to our mathematics, that they are very sound, this will be reflected on the non-homogeneous term of the differential equation, and that's gonna give us a non-homogeneous term, which is, it looks like, right? Now, so if we think, or we want to solve this initial value problem using the Laplace transform, on step number 1, we'll be taking the Laplace transform of this, which will entail on finding the Laplace transform of things like this, right? So that's what we are going to learn on this section. How to compute the Laplace transforms of functions like those, right? Let's start with a simple one. So suppose let's call this T axis, vertical axis, and then stays at 0, right, up to here, and then it jumps up to level 1. You call this function, because that's a, at some value a, could be anywhere positive, 3, 5, whatever. So thinking of those terms, if that would be the non-homogeneous function, means that from time t equal to 0 to time t equal to a, the switch is off. No